Okay, welcome back to Toronto Air Seminar. Today we are glad to have Brian Okorn to give a talk on object representation without direct supervision. So Brian Okorn is a PhD student with David Hill and Marshall Albert at the CMU Robotics Institute. He studies zero-shot and self-supervised object representations for robot manipulation, with the goal of allowing robots to intelligently interact with novel objects. Prior to joining in CMU, Brian worked as a researcher at US Navy SPAWAR, developing 3D mapping and registration algorithms for unmanned ground and surface vehicles, and has worked with the Johnson Space Center and the NASA NSTRF Fellowship. Brian Okorn was also my mentor during my master's at Carnegie Mellon. I'm very grateful for his mentorship, and we have collaborated on several exciting projects. So looking forward to your talk, Brian, and feel free to take it away.
Excellent, excellent. Like Zhao said, we've worked together a lot, and actually both of the projects that I'm going to be talking about, one being the extension of the other, are projects we both worked together on. So like Zhao said, I'm going to be talking about object representations without direct supervision. And so when you have a robot interacting with a scene, invariably you're going to be interacting with a large number of objects. And when you need to actually interact with these objects, you need to have some way of representing the objects. And there's a lot of different options for representations. You can use detection bounding boxes, 60 object pose, key points, or latent representations. But in this talk, we're going to be focusing on some very grounded representations, those being the representations of 60 pose and object detection. And towards that end, we're going to be looking at two projects that we worked on. One focusing on estimating the pose of unseen objects. This is ZePHyR, zero-shot pose hypothesis rating. This is work that was in ICRA last year. And then we're going to be working on it. We'll be talking about an extension to that work where we're taking our zero-shot poses and trying to self-supervise detections using them. And that would be OSSID, online self-supervised instance detection by and for pose estimation. And this will be work that will be presenting in ICRA coming up, and is also in RAL. So we're going to first focus on the 60 object pose representation. So what this basically is, for those who don't know, is it is the translation and rotation of an object with respect to some object model that you have offline. And the goal of 60 object pose estimation is to find the object that you're looking for in the scene and estimate its orientation and translation with respect to some model you have the object on the robot's side. And the reason that we want to actually look at this is because it tends to be very useful in manipulation pipelines. And so this is the general way that this fits into the object, the manipulation pipeline. First, you have some input image of the scene with clutter and the object that you want to find. You pass this through some object pose estimator. You compute the pose of the object in the scene, and then you pass this pose off to some planning algorithm that can do some pose relative action to it. And the benefits of using pose in this case is it directly maps to the end effector control of the robot. If you have the object in the gripper of the robot, you're directly controlling its pose. So if you're trying to mimic the pose of a demonstration, you have full control over this representation. Additionally, if you have any annotations on the object or any annotated grasp locations or important points on the object, you can directly compute them in the robot's frame by just using the pose estimate that you've generated from your pose estimator. And so how do we normally handle these pose estimators in practice? Well, most of these are deep learned pose estimators. The best state-of-the-art methods right now are, and they all tend to be object specific. And so you have to do object specific training. So you have some object that you want to interact with in the scene, say this Cheez-It box. And in order to actually train a pose estimator, you need to have some annotated data set. In the past, this had to be human annotated data sets, but nowadays these are becoming more and more commonly synthetically rendered data sets. You annotate the pose of the object in the scene, and you need to train a specific pose estimator that's only designed to find that one object. And if you have to find other objects in the scene, you have to repeat this process, annotating more data, generating a new pose estimator for every object that you're going to want to interact with. And this doesn't really scale well to large numbers of objects. You end up with this excess effort in collecting data for each object if you're not using rendered scenes. And even if you are using rendered scenes, you have this excess time training the network on each object. Every time you have a new object that you're adding to the collection of objects that you're going to interact with, this will take training time. And then every one of these objects will have its own specific region of network weights that have to be trained for it. So this really doesn't scale well as the number of objects that you interact with grows. And for most robots that we're working with, they'll be interacting with an arbitrarily large number of objects. And so we're seeking to improve on this, all these problems with ZePHyR, a zero-shot pose estimation method. And so zero-shot pose is specifically a pose estimation where you're trying to generalize to objects that you haven't seen before. So you take information that you've learned on seen objects, say some set of trained objects that have some labeling, and you want to learn a pose estimator that can work on objects that you never saw before. And so you want to be able to do this with no new training data. You don't want to be adding new labels to your scene, to your data sets. You just want to be able to start with some set of objects and learn something general enough that it abstracts to a new set of objects. And so there's been some work in this field. There's some work on learning multipath encoders that take a bunch of different object views, map them into a similar latent space, and you can use that latent space to estimate the orientation of objects. Latent fusion develops a 3D latent representation of the object that it then uses to do pose estimation on this novel object. Pose from shape takes both the 3D shape and some image of the object, maps them both into some latent encoding space, and regresses orientation. But the problem with all of these methods is they really aren't designed to handle clutter well. Largely, they either require some amount of segmentation of the scene or require the scene to have really no clutter in it and really only the object in question. Now, as opposed to the deep learned methods, there are classical methods that kind of are inherently zero shots. A lot of classical methods are based on purely geometry and have no learned components, allowing them to work on arbitrarily new objects as you see them, but they don't tend to be as accurate as the deep learned methods. So the method that we're going to be looking at here is point pair features. And these are a set of features that are generated from pairs of points in a point cloud with normals. So you have sampled points pairs with normals, and we're going to be trying to learn, or trying to compute statistics on these points that are invariant to transforms and rotations. So the statistics we're going to be computing are the distance between the 2 points, the magnitude of this vector between the 2 points, the angle between the normal of the 1 point and this vector, the corresponding angle with the other point in this vector, and the angle between the two normals. And given these statistics, we now have a 4 vector that is invariant to any transforms to these points. And so this will be constant regardless of what pose the object is in. And you can use samplings of these point pairs to match between some model that you have of your object and an observation, and then generate a bunch of geometrically plausible hypotheses through voting methods. And while this seems like a relatively kind of simple method, even a few years ago, it was some of the top performing methods on the BOP leaderboard. Now, these methods are perform pretty well, but they don't really compete with deep learned methods, which are able to outcompete them with respect to accuracy. And so what we're
Brian,
seeing, oh yeah, go ahead.
I think there's a question in the chat.
Oh, sorry.
So why would you need object-specific pose estimator? Shouldn't a more general purpose network better to train and learn across categories? I thought
Yeah.
the general network was the default way to solve this problem.
So there are category-specific networks to do this. And so you're basically going to learn a pose estimate that works for like all cars or all like pill bottles or all kind of mugs. But there doesn't tend to be a lot of methods that work for arbitrary poses. The closest thing that I've seen in a while was DeepIM, which is something that does like an iterative approach of estimating the difference between a rendered image and a model, but that doesn't actually end up producing very good results in kind of cluttered scenes when it wasn't trained on the specific objects that you were looking for.
I guess there's also like one inherent problem, I guess, with open world object estimation, pose estimation. If you've never seen the object before, there is no way of deciding what the reference pose is. So if it's the first time you're seeing an object, it's like an ill-posed problem in some sense, unless you say this is for me now the zero pose and store this in some database.
Yeah. So this work is at least assuming that you've generated some model of it. You can do that like online pretty quickly.
Which for warehouses is perfectly sufficient, for example.
Yeah. Although for what you're talking about of generating a reference pose, there is some future work that the work that is in RSS is actually looking at how you deal with like unknown reference poses and what to do with it. So it's actually a very interesting question, hopefully, that I'm happy to talk about afterwards.
Okay.
Yeah, but in this work we're assuming. Yeah, sweet. In this work we're assuming that we start with some kind of 3D model of the object, whether or not you've generated it from like a rapid scanning method, or if you have it like from warehouse. So we're assuming you can store some subset of object meshes, or at least query them relatively quickly, but we're not trying to train on those object meshes. And we want to generate a large number of plausible pose hypotheses, potentially from point pair features or other kind of hypotheses generation techniques. And then we want to actually see which one of these hypotheses best matches our data. And we want to score them according to that, pick the one that's the best score, and use it downstream in our task. And so really the big focus of this work is how do we score pose hypotheses? And this has been kind of a classic problem in any kind of camera pose estimation or registration work. And the very, very traditional ways are you do some kind of inlier counting according to some hand-designed like distance function. In the purely geometric case, you're going to use geometric point error based on some model of the object. But in some more recent work, DSAC learns a scoring function for camera pose estimates. This is a differentiable ransack method where you can essentially learn this kind of scoring function for camera pose estimates. And then there's also been some work specifically with poses where they're trying to learn an error estimate for reprojection error. And while these last two are learning some function, the pose proposal critic isn't really generic to objects and isn't designed to handle very far pose estimates. And DSAC was designed to handle basically camera pixel correspondence errors. But we're going to try to start from this idea of learning the scoring function, and we want to see if we can learn it such that it generalizes to new objects. Yeah. And so this is the basic idea behind ZePHyR, the zero-shot pose hypothesis ratings. So given some observation of the scene, in this case, we're looking at RGBD observations and an object model. So again, we assume we have some object model that we're working with. All of our poses will be relative to this object model. So we have a reference pose that we're defining as our origin frame, and it's whatever frame you define on your object model. In this case, we're looking at the object model as a set of oriented colorized points. We're going to generate a pile of pose hypotheses based on some hypothesis generation method. In this work, we were looking at point pair features with also oriented SIFT features as an additional set of pose hypotheses to work with. And so once you have a set of pose hypotheses, you want to compare them to your observation using very simple distance functions to generate some point differences. And the goal of doing this with these point differences is to force the network or prevent the network from overfitting to any individual object that it sees. We're trying to somewhat limit the information the network can work with. We're going to take these point differences, push them through a scoring function, and compute a score for every one of the poses that we've seen. Pick the best scoring pose, and that's the one that we're going to say is the pose of the object. And so that gives you kind of a general description of what we're doing, but now we have to train it in a way that it's zero shot. And so to do that, we looked at two data sets that are very commonly used in object pose estimation. The YCB video data set, which is a very large data set of textured objects in mildly cluttered scenes. Most of the scenes are roughly about as cluttered as you can see here, where there's mild occlusions between the objects, but it's not heavily occluded. There's about 21, there are 21 objects in total in this data set, all with pose estimates, or all with pose annotations with them. The other data set we're looking at is a little bit of an older data set, the Ocluded Line MOD data set. This is much lower texture objects with heavy occlusions in the scenes. And the way we're going to train these in a zero-shot method or manner is we're going to take these data sets and we're going to split them. For specifically the YCB data set, we're going to split all of the objects in two, taking them each independently as their own training sets, and then we're going to cross-validate them on the other sets of objects as their test sets. And so in this case, none of the annotations for each half of the network, or each network hasn't seen annotations for the test objects in training. And for Ocluded Line MOD, we're going to be using the actual fuller line mod data set, which contains more objects than just the 9 in the Ocluded Line MOD. Specifically, we're going to be using the ones in the synthetically rendered data set as our training set. So these are not annotated in the scene. And then we're going to be testing on the specific Ocluded Line MOD real world test set. And so,
if I may ask a question here,
yeah.
for your training and evaluation protocol, where you have only these two, where you basically divide it in two sets, are the results very different between the one set and the other, or were they somewhat similar?
They are pretty similar. They were, let's see. I'll show that up here. They were, yeah, within one object set was a little, slightly easier, but it was within 6 points of each other between the two object sets with respect to the average recall score. Yeah.
Okay.
So relatively, there's slight differences between the sets, but not a a wild swing between them.
So the difference between methods was larger than the difference between sets, is what you're saying?
Yes, yeah.
Okay.
And largely we tried to keep the like set of objects relatively similar-ish between the distribution. And by similar, I mean we wanted equal numbers of symmetric and non-symmetric objects. So in YCB specifically, you have some rotationally symmetric objects with this block and these things. Yeah.
So
and
this
then a
was a
bunch of-
handcrafted split, basically, to make sure that they're similar, the splits.
Yeah. We didn't try too hard on it.
Makes sense.
It was basically just equal number of symmetric and non-symmetric objects. We didn't want one to be all non-symmetric and it never have seen a symmetric object before.
Makes sense.
Yeah. And so the base method that our method is based off of is DROS. It's a point pair feature method using only the geometric features that we've described. And it's able to produce a pretty decent result on the YCB video data set. And once you add our scoring metric, you get this 50% increase on this data set. And this is pretty obvious that it's going to happen. The core geometric features have no notion of texture to them. And so basically getting any kind of color information is going to give you a huge boost in this scenario. We also see improvement over the proprietary point pair feature method that was the best one at that time. And then additionally, we compared to one of the methods that is actually designed to be zero shot, this multi-path method. It unfortunately relies on having good segmentation masks of the objects. And so even using ground truth segmentation masks and picking the best matching segmentation mask for each one of the poses, it does far worse than even the geometric methods on this cluttered data set. And then finally, just kind of a ablation test comparing our hypothesis scoring method to just this simple like standard ransack style. If you just compare to depth inliers, you do very, very poorly on this thing. So you actually are benefited from learning something reasonable in this scoring function. We see similar results in Ocluded Line MOD, although you get less of an increase in performance. This is largely because you're not getting as many textured objects in Line MOD. Most of these are very geometrically unique, so your geometric-centric hypotheses are already pretty strong in this case, but you're still getting improvement in that case. We even see improvement over the kind of proprietary point pair feature method, and then the kind of standard zero shot methods just don't really succeed on this data set at all. And so to get an idea of how well we're doing with respect to seen versus unseen objects, are we just learning something that's just working tremendously good on the objects that it's trained on, and it isn't real, and then is just like, because we were doing so well in trained objects, it's doing slightly well on the new objects never seen before? And that's really not the case. We're only getting a 4-point drop in performance when you map from objects that you were trained on to new objects that you've never seen before. And so we really are learning something that maps over between objects that you're trained on and novel objects. Now, for a little bit of a visual idea of what's going on, this is what your baseline hypothesis selection would be with the DROS features, and this is what our method would be producing, or our method produces in the same scene. And so you're getting these just completely kind of incorrect pose estimates when you're dealing with large, like very complicated clutter. And we're able to match multiple objects that were incorrectly estimated in the original set of hypotheses. So if you use the purely geometric hypotheses generated by the point pair features, you fail. In our case, we succeed in a lot of cases, although it's not perfect, where we're still getting some mistakes when you have very, very heavy occlusions. Similarly, improving over the baseline, over multiple objects, but we're still getting these kind of few incorrect poses whenever things are very, very heavily occluded. So this isn't the perfect solution. In most cases where you know the objects that you're going to find ahead of time, you're going to get more accurate results on something object specific, but for the most part, this is doing a very good job in this data set and is outperforming other zero-shot methods. Now in YCB, where we actually saw a really, really large improvement, you're getting a lot of this improvement due to objects that are geometrically symmetric, but texturally non-symmetric. So sometimes you get completely wrong results where the flat areas in objects map the flat areas in tables. Our method improves them, although again, not completely perfect, where it's not mapping this little clamp to the right position. But you see more of these kind of geometrically reasonable solutions in the baseline that our method fixes to texturally correct solutions in our outputted correct or our outputted pose estimates. You see this across the data set where it's doing these kind of it's basically matching the geometric symmetries, but failing on the texture mapping, and we're succeeding over that. But again, we get some mistakes in symmetries and some just complete wrong answers. So again, not perfect, but we're producing pretty good results. And one more thing you can do with this, because we're doing these kind of pose hypotheses methods, where we're generating pose estimates and we're scoring sets of pose estimates, you can do essentially a particle filtering style approach on a set of hypotheses. So this is some visualization of doing particle filtering on video data sets. Here we have all of the pose estimates that are generated by Dross, scored by our method. Blue is very, very low scoring pose hypotheses. So these are just completely unreasonable. And as such, they're very, very down weighted. And what we're going to be doing is we're going to be sampling, selecting the best pose, sampling around it. And then about every 10 frames, we're going to re-sample the whole set of poses, pick the best one and sample around it. We're able to track this object through the scene. And again, this is an object that the estimator has never seen before at training time. We're able to track it pretty well over time, keeping all of the pose estimates pretty well scored around it. And this also works on objects that were generated by, or objects whose meshes we generated at training time. And so this drill isn't part of any of the data sets. We created a hand-built object mesh of it. It's obviously not a very accurate mesh. It has a ton of holes in it, a lot of artifacts in it, and our method is still able to track this object through the scenes, largely correctly estimating it. Even when it loses track of it for a second, it's able to pick it up again very quickly. And so what are some of the intuitions that we're getting from this method that give us this ability to generalize to novel objects? And it's mostly coming from this limitations that we're putting on the network. So we're forcing the network into isolated point differences. In this case, we're looking at element-wise color differences, the signed depth difference between the projected points and what we're seeing in the depth image, and differences between the normals computed on the model and the normals computed on the depth image. And specifically of these features, the color images are, or the color and the depth are producing the best results or improving our method the most. When we remove them from the method, we're seeing a 11-point and a 9-point drop in our performance. Whereas when we remove the normal information, we only see a 4-point reduction. And so largely, you're getting your benefits from geometric and color information. The normal information is also giving you some benefit, but if you needed to cut it with respect to some kind of processing, it could be done. Another important feature of this is how we're actually doing the scoring. So we're actually taking these points and using their pixel coordinates to pass them through a PointNet++ to compute our actual scoring function. And this is kind of a bizarre way of handling image information. Normally, if you would have these kind of pixel information, you would pass it through a CNN, but passing it as point difference or as points information helps the network understand the local structure while still giving it some geometric information about where the points are. And so if you look at different ways you could actually handle this scoring, are the method we actually use, the PointNet++, you're looking at geometric coordinates that define where the points are. And all the points have some kind of local structure. And if you were to remove that local structure, say with a PointNet, just a standard PointNet, which you're still using your geometric location information, but you have no local neighborhoods, you're just using global positional information, we see a pretty drastic decrease in performance. And additionally, with a CNN, which is still has some local pixel neighborhood structure, but isn't looking at things as geometric points, we also see a similar reduction in performance. And so really treating these things as local geometric regions is a key to how this method handles novel objects. And then finally, we specifically are looking at a loss that's with respect to this pose error that we're working with. We can do the error of all the points in the scene for the trained objects to compute some pose error associated with them. And then we're using this this error in expectation to sampling according to our scoring function. So this is a similar methodology that you see in DSAC and you see in reinforcement style approaches where we're looking at the expectation of our sampling distribution. And in this case, we're not looking at the expectation of the actual error, but we're looking at the log of the error, because really what we care about is the differences when you're really close to zero. We really don't care about getting the score of a bad thing and a slightly worse pose. What really matters is that you get the score of the best pose correct. And so we don't want to be really over penalizing a method for getting something that's 2 meters off versus 5 meters off. Both of those are terrible, and so they should be treated roughly equally. And again, we're only really picking that last best score. And so these all of these parts enabled us to be able to learn a zero-shot method. But what are the limitations that we're seeing in this method? Well, it does have some limitations with respect to accuracy when you're comparing to object-specific methods. One of the major limitations we see is speed. When you have to actually estimate the hypothesis, a large number of hypotheses in some complicated data sets, such as line mod, we actually have to use fairly complicated or fairly aggressive hypothesis generation parameters in the point pair features, which takes a large amount of time. And so that's largely because you have to search over this whole input space and produce point pair features of the whole input space and do voting over all of those points. And so really, a benefit to this method would be something that could reduce its search space. So that's where our next method comes in. This is the method that we'll be presenting at ICRA, OSSID, online self-supervised instance detection. And the idea here is that given our observation, we also want to have a zero-shot object detector so that we don't have to search over the whole space. We can find the object in the scene, crop the image down, and now we have a very, very small input space to generate pose hypotheses for. We can basically use as many pose hypotheses really as we want in this small space. We can pass it to our zero-shot pose estimator that we've just described and estimate the pose of the object in the scene. And ideally, we want to be able to improve our zero-shot object detector using our 6D pose estimator, and subsequently keep using this more and more accurate pose detector to reduce our search space. And that's the idea behind this work. So given some observation, we're going to be freezing our zero-shot pose estimator, do some detection in the object scene. Then we're going to be using the pose estimates as pseudo ground truths to improve our zero-shot detector. And so there've been some work on zero-shot object detectors. In this case, we'll be looking at DTOID. This is a method that takes in some object templates and estimates basically compresses these templates into convolutional filters, passes them over the input image, and is able to take an arbitrary template and compute a segmentation and a bounding box for that object. And so really the important idea behind this is we have some template image and we have some observation. We're going to pass them through a network, find a correlation between them, and find that object in the scene. And if we change the object template, we're going to change the object we find in the scene. And so if this worked perfectly, this would be great. We would be done. And in line mod, it works pretty well. But when we've tried to transfer this to other environments, it actually seems to fail pretty hard.
Wait, what was it with YCB? You had like much fewer objects in total as line mod, right? A better resolution, but there were fewer. Or how many objects were there in line mod? Can you remind?
Yeah, line mod has 9 objects in Ocluded Line MOD, 7 additional objects in the full line mod data set. Yeah, they're
here you transferred the model trained on line mod, or you did retraining for YCB and it just didn't work?
In this case, we did retraining on this YCB, and weren't able to get it to achieve the same results on the YCB data set. And
oh, wow. It's like a big divergence.
It's huge, yeah.
Interesting. Well, what is your feeling what the reason for this might be?
I think that it might have to do with,
yeah, actually, like for DTOID, we are training this on a synthetic data set as reported in the original paper. So the original paper didn't release their training data set, which is purely synthetic. So we have to reproduce the synthetic data set ourselves by like rendering a bunch of objects into a cluttered background. But somehow like the training on that synthetic data set didn't reproduce good performance on YCB video. Yeah.
I think maybe YCB actually suffered from the fact that it has textures. So the network was good enough to capture a non-textured object, but then once textures were there, it became hard.
Yeah, you have very significantly more complicated textures in YCB. And you also have a lot of relatively similar-ish objects. There's a lot of block boxes, so you can easily get like misdetections or detecting the wrong objects as the wrong type. So the goal, we like this approach of passing in templates, generating features, and then using detection. But how can we get it to actually work on the data set that we're trying to use? And so we're going to be doing using our pose estimates, which we already know can produce good results on this data set and produce pseudo ground truths. So taking our pose estimate, we compute a segmentation mask for it and subsequently a detection bounding box. And we can then supervise our zero-shot method on this data set or on this pose. And so it's important to note that while we're giving this a pseudo ground truth, we're not actually using any annotated poses. These are purely zero-shot predicted poses on this data set. So there's been no labeling, whether via rendered data sets or human labeling. But as you saw previously, our method's not perfect, so we can't just use every pose that we have. And so we have to decide which poses are good poses to use. But the method that we were working from is at its core a scoring method. We're trying to rate the accuracy of each one of these poses. And so we can see that the average pose error for any one of our actual estimated poses versus what the raw ZePHyR score was is shown here. And before, we were only picking the best ZePHyR score. So it didn't matter if we had a very, very low ZePHyR score, if it was, or the low confidence score. If it was the best one, it was what the pose was. But now we can be a little bit more choosy, and we can say not select any of the poses that were very, very low confidence. And we can see that there's this kind of obvious demarcation between low confidence, high error poses and high confidence, low error poses. And we can just basically focus in on these good high confidence poses. We can fine tune the detection network using only these poses. And so, as you saw previously, we had really poor results on these data sets. And if you fine tune on them, in this case, on an online fashion, as you see more data, the pose estimator passes the best pose estimates to the detection network and fine tunes it on it. We produce a drastic improvement on YCB, the YCB data set. We also see a pretty good improvement on the DTOID data set as well. And if you're using this with our pose estimators, the baseline method that we're using our pose estimators, if we then use those detection bounding boxes to isolate only the regions that we think the object's in, we actually get a small amount of improvement on our pose estimates. But most important on this is not that we're trying to get an improvement here, it's that we're not actually reducing the accuracy. So we're cutting down the input space, but we're still maintaining our accuracy. We're getting slightly more accurate results, but it's more important that we're just basically equivalent in this case. And the reason that we care about that is now that we're isolating down into the smaller pose space, we can get very, very drastic speed ups. In this case, with line mod, we're getting a 10x speed up by just culling away all of that extra input space that our detector doesn't think the object is in. And as we see more and more data, as we're training online, we start out, and this is the untrained network on YCB. You start poorly, and as you see more and more data, you do better and better. And to get like a little bit more in-depth view of it, this is on the line mod data set. And so in this case, green bounding boxes are the correct matches. Blue bounding boxes are things that the detector detected that either aren't objects that we care about or were classified as the wrong object. And then red boxes are objects that it missed the detection on. And so it should have detected something there and it didn't. And so this is the results that we're getting on line mod without any fine tuning. And as we see just a little bit more data, all of our bounding boxes become slightly better. We're finding more objects. We're still classifying some of them wrong. With a little more data, we're doing better. And with all of the data, we're doing really good across the board. Not perfect, but most of these are doing pretty well. Similarly, when we're looking at YCB, as you can see, it is detecting some objects, but actually in this case, it's straight missing a large number of the objects in the scene. The red boxes, again, are where it should have detected something and it hasn't. And the blue boxes are where it's detecting something that it shouldn't. So you're getting like just completely incorrect detections. And just with like a little bit of data, you're improving the results. And just a little bit more data, things are almost perfect. With only like two-thirds of the way through the images, we do get some degradation in this case with heavy occlusions, but for the most part, the method produces extremely accurate bounding boxes by the end of seeing all of the data. And if you wanted a kind of like upper bound on how well this kind of system can do, you can look at transductive learning, where you basically give the network all of the data that it's going to be tested on at test time at once. It can do this kind of detection estimate, this detection fitting on all of the data, and see how well it could do on that data. And so while this is not actually something that is easy to do in practice, because you have to have all of the data at once, if you wanted to kind of offline estimate poses on a data set, this is about the upper bound of our method. So really the online method is doing pretty well in comparison to that. And so the things that we've seen so far is that we can, or in this talk, is that we can do zero-shot pose estimation that can generalize to unseen objects if we really just try to learn a comparison function and a scoring function. And if we isolate the information that the network is getting, we can prevent it from overfitting to any of the things that it sees in training time. Additionally, we can use pose estimates to supervise a detection algorithm, and we can use specifically the zero-shot pose estimates with our scoring function to produce very accurate detection pseudo ground truth. And then finally, we can use that learned detection to drastically improve the inference speed of our method, producing a significantly faster pipeline overall. And so I'd like to thank the co-authors and my sponsors that made all of this work possible, particularly Chao for all of the work that he's done on these projects. And happy to answer any questions that I wasn't able to answer during the talk.
Thank you, Brian. Thank you, Brian. Thank you for the great talk. Yeah, any questions from our audience?
Yeah, I have. Thanks so much again, Brian. This was a really amazing talk, and thanks so much for letting us have Chao. We are very happy to have him at U of T.
I'm very excited to see what he does next. Chao is a truly great person to work with. This work would not be possible without him. He's first author on the second work too. He's done amazing work.
Yeah, we're very excited to have him. I have a more broader question. I worked a little bit on pose estimation, but some time ago, on like very specific things. And if I look like at, there are like now a big bunch of companies, probably the most prominent among roboticists is Peter Abil's company that work on grasping.
Yes.
And I wonder, he speaks sometimes to their pipeline, but I wonder to what extent pose estimation is used in these grasping pipelines. Like some people go directly with some sort of end-to-end variant where pose estimation might not even be used to begin with. So maybe a question that, I was thinking about recently, like self-critically, like what do you see as the potential of pose estimation? It's definitely an interesting research question, but do you see application potential for it? Is the reason why it's not as much used as we would have maybe expected? Or maybe it is much more used, and my assumption here is wrong. Like, yeah, what are your thoughts about the pose estimation and practical applications of it?
Yeah, so my personal opinion on any representation is very, very dependent on what your goal is. And so pose estimation is important if pose matters. If the actual alignment of things matter, then pose estimation is important. Like, so if you're trying to do potentially complicated interaction between objects, pose is a useful tool for that. But if you're just trying to grab something, all of the best methods that I've seen that do any kind of grasping, they really don't care what pose the object's in. They just grab it, and they grab it in the most grabbable part. And so if the goal is purely to get the thing in your hand, you don't need the pose, like completely unnecessary. But if you need to grab it in a certain way, so if you're trying to use a tool, you can't just grab the tool by any arbitrary point. You have to actually grab it in like a usable manner. Then pose estimation is valuable. Now, largely, I am not sure pose is really the best representation for a lot of things. Key points are pretty useful. That can cover kind of a similar idea of pose. It's like a more distributed variant of pose. You can use constellations of key points to estimate orientations on objects. And then actually scene flow is another thing that I've worked a lot in. And I'm starting to think that scene flow might be a good representation if you're trying to interact with objects that either are articulated or are soft, or even rigid objects. Like scene flow is something that generalizes pretty well across objects and can give you some of the same benefits as like rigid pose. So it really depends on kind of how precise your interactions need to be, how much say orientations have like matter to your problem. So if you need to like align an object in a specific orientation, whether it be like trying to put an object like in a specific position on another object for say like a assembly task, then pose is valuable. If you're just trying to grab things and put things in boxes, pose is it's essentially you've overcomplicated the problem. And in that case, I would probably focus on detection, segmentation, and graspability. So your representation would then just be a seg mask.
Yeah, I mean, I had a similar feeling. Even for tool use, I sometimes wonder. So basically, you know, all the manipulation research goes like down the route that even things such as tool use are at some point trained end to end. So while pose is an important information, instead of explicitly supervising it, I wonder whether for certain types of tools, pose will be just implicitly learned as part of the manipulation learning process. But this I'm saying not as a criticism. I'm still very excited about the problem. I'm just looking more for, you know, where will be used.
Yeah, I tend to still think that at least some amount of grounding is valuable in your representations. And so I'm not like completely sold on the full latent representations where we just learn some arbitrary latent representation on an object, and then we use that in some deep learned downstream tasks. You kind of cut yourself off in those ways from doing like classical planning and classical like control, which for a lot of problems very well solve the problem. And so while you've kind of like added potentially some more complicated kind of losses and training from, or remove some of those more complicated training from your pipeline, you kind of lost the ability to handle like what would have been already solved problems.
Yeah.
Yeah.
And I guess pose is always on a helpful auxiliary signal, probably.
Yeah. Yeah. It's
at the very least.
Yeah. I don't think so. Going forward, I'm actually not working with pose as often. And I'm not as sold as it being like a good end-all be-all representation. I think it's kind of a little maybe too rigid. But I think having something that can map to pose, or it can be in some way like directly supervising your representation helps. Because there's at least some of the like, say like differential ransack, which is they looked at fully end-to-end supervising some of these methods, and they found that you actually do a lot better when you can just like, okay, this all this can be end-to-end supervised, but really if we supervise this part, supervise this part, supervise this part, all with their own like actual set losses, and then put it all together and then do a little bit of fine tuning on the full system, you tend to get better results.
Yeah, and I guess also another thing where there is hope for pose is when you, I mean, in all these graphic C robotics approaches where you want, you know, when you start with some sort of nerve-like representation and you want to manipulate objects or to edit them, you need to have at least some sort of input to how you edit them. And one of many things that you would want to edit is obviously like the object's pose. So you need to have some sort of reasoning about it, I guess.
Yeah. Yeah. So I don't think pose is dead, but also it's not the end all be all.
Yeah. That's, I think, a good conclusion.
Sweet. All right. So
Any other questions?
Yeah, any other questions, or do you want to just chat about, you know, whatever? All right.
Yeah, if no other questions, we are almost we're also almost at the time.
Oh.
So we can also end here.
Sweet.
Yeah, great. Thanks, Brian. Thanks for a great talk. And
thanks for the amazing talk.